So this talk is going to be about formally verifying functional correctness um, in a quantum world. So what does this mean? Of course, as we all know, quantum computers are possibly at least coming, and we need to prepare for them. And we are implementing a lot of new post-quantum encryption algorithms to make prepare for this. But implementing this has to happen fairly quickly because yeah, these quantum computers might come sooner than we'd like. Um, and how do we then make sure that this implementation effort uh, happens with as high assurance as possible?
So, Oskar, could you briefly introduce yourself as well for the
Oh,
record?
yes, sure. So I'm Oskar Goldhahn. I'm a PhD student at the NTNU in the NACL group, researching mostly voting schemes and formal verification. Yeah. Um, so my talk will be structured in the following way. I will start with some formal verification basics. Then I will be going into some technical details about some ways this is being done. Um, Including but not limited to basic core logic. And then I'll be expanding a bit on how this works for uh, the quantum future. Yeah. So this last part is not necessarily relevant to what I mentioned at the beginning, but in the future, if we also want to implement quantum algorithms, then this will become much more relevant. And also for modeling the random oracle model and quantum adversaries and so on. Yeah. So I was a bit unsure about the level of talk I should give here, so I'll start a bit soft at the beginning. What's formal verification? And broadly speaking, the goal of formal verification is to make sure that programs are correct. So there are a bunch of different approaches to achieve this more high-level goal. Of course, we have tests, we have dynamic analysis tools like Valgrind and so on to ensure that memory accesses are being done correctly, and a bunch of other properties. And there's a lot more tools than this. Um, but with tests, you can only test so much, and you cannot exhaust necessarily the entire space of possibilities. Um, you're usually, with the basic test, you're just testing one point usually, or one trace. So then you have property-based test and fuzzing, which expand upon this by running a lot of different traces or um, testing with random inputs and so on. But for cryptography, this isn't good enough either, because if there's one input which behaves badly, then the adversary might be able to find this. Um, so we have even stricter tools. And there's a gray zone here. Some static typing tools are not sound. They have false positives and so on. But there's a bunch static type analysis tools out there that are also sound, which if they produce an output, tell you here's a bug, then you know that there is something wrong. And of course, you have static typing. A lot of tests in, for example, Python are just to test that the types are correct. And with just static typing, you can uh, avoid the need to write some of those tests. And depending on the strength of your programming language, you can have more and more things that are known about your program, depending on your types. Uh, like in proof assistant, which allow you to prove basically anything you like with your types. Um, yeah. And then we have proofs that can be written or generated. And some of these static analysis tools also work with proofs, but kind of hide them from the user, or they at least rely upon the theory where these proofs are written for their proofs of soundness and so on. So this is kind of the basics. And there's a bunch of tools out there. There's languages that allow you to write these proofs, and some also allow you to write programs that you can execute in reasonable amount of time that's compiled to reasonable machine code, like F star. And then you have things like ROC, formerly known as COC, which is a proof assistant that's more broadly used in lots of mathematics and computer science, and proof languages like EasyCrypt that are more focused on cryptography and specialize in proving cryptographic properties like security and so on. And then you have some tools which allow you to prove properties about your regular programming language. Some of them work by translating from some other programming language into a proof language, like Jasmine translates from the programming language Jasmine into EasyCrypt, and then you can use your EasyCrypt tools to prove stuff about your resulting translating program. And then you have Hacks, which translates from Rust into, I believe, F star. And yeah. In addition, there's analyzers, which also have some internal representation, but they don't necessarily um, translate to a different language where you then write your proofs. Usually they work by requiring you to annotate your original source code, which um, then is being checked that these annotations actually um, are true. If you have some precondition, then some post-condition will hold, and you can annotate all your code in the middle to help these analyzers prove the tools, prove the results. Sorry. So any questions about this more general state of things before we go on to more of the underlying theory? No. So I planned this talk. Um, this talk is planned with questions in mind, so hopefully we'll have some questions. I held a similar talk a week ago at our cryptography group in Trondheim, and I had a lot of questions about the underlying theory. So if you have some questions, please ask. This can be a bit confusing to those who are not used to this way of thinking about programs. Okay, so how do we actually model computation in a way that we can reason about formally, that a way where we can use the computer to prove results and so on. I will be using the wire language as an example, but the concepts here also generalize to other programming languages. Of course, you will have other complexities introduced if you have pointers and all this other stuff going on, which can make things quite complex. And often because of that, you see that the analyzers will only restrict to a subset of the language to make sure that things are simple enough to deal with. But yeah, even then, you can often extend your reasoning tools to handle more and more of the language. Okay, I need to move this. Okay. Yeah, so the language that we were looking at has a few instructions. You have the skip instruction that does nothing. You have the abort instruction that just aborts the program. This is to model things like non-termination. Abort doesn't terminate, weirdly enough. And then you have assignment, where x is a variable, e is an expression. And you can compose these programs. First execute one thing and then another. You have branching. If some expression evaluates to true, then you evaluate the first program. Otherwise, you do the second one. And while loops. And of course, structured program is a lot easier to reason about, which is why this is being used here. And upon this, we will build some rules for proving things. But yeah, first, what are programs? And how do we model state? Usually we model state as a function from variables to values. And there has to be some typing on top of this as well in most cases to make sure that the variables have the right type. But I'm kind of shoving that under the rug for now. And for deterministic procedures, which is what we'll be addressing here at the beginning, you have a function from states into states or this bottom symbol, which indicates non-termination. And you need this because you have while loops, which means that your program might not terminate. Yeah. And for niceness, if we let expressions include variables, which are then substituted by the values in some, it's supposed to be sigma, not m here. So you evaluate the expression with this state to get the value of this expression in some state. Yeah, so this was a bunch of like overarching stuff and definition of the syntax. What does this actually mean? So what we usually do is we define some semantics for our programming language. And this is the notational semantic, which means it kind of treats it in a mathematical fashion. What does skip mean? What does it do to states? Is kind of how you define the semantics here. So skip does nothing. So if you have some state to begin with, then after you do skip, then you still get the same state. And for abort, you have some starting state, sigma, and then you end up in the bottom kind of state, non-termination. For assignment, you take the state and then you assign the evaluation of the thing that you assign to x into x. So now the state has the value of e in the starting state instead of whatever was in x to begin with. And then we have composition. If so you first evaluate the first part, if the state afterwards is bottom, meaning it didn't terminate, then the composition doesn't terminate either. And otherwise, you continue with the next part, and the resulting state will be whatever that output from the intermediate state. For branching, we check the branch condition and decide which program should be used to modify the state depending on this. And then we have the while loops, which are a bit more complex. I use the supremum operator here for reasons that will become more obvious later. And we define it as a limit of if statements. So say if we have if we know that the while loop will only take three iterations to terminate, for example, then that is the same as having three if statements with the branch condition being the same as the loop condition for the while loop. So this is kind of what we model here. We continue iterating n times, and then if we still haven't broken out of the while loop, we terminate. And then we take we don't terminate, sorry. And then we take the limit of this as n goes to infinity. And this turns out to be well defined because you'll only be be adding these aborting cases as you increase n. They will now, instead of abort, they will continue running for one more iteration and then one more and so on. And this supremum, formally you take bottom as the bottom thing in a partial order, and then everything else is ordered above it. So you have a sequence of either bottom or some state, and when you take the limit, either if everything's bottom, you still get bottom, or if at some point you get some non-bottom thing, then you will stay in that state. And of course, you also need to prove that this actually does converge, but it does in this case. Yeah. All right. So this semantics is a bit complex to reason about directly. So what we do is we use this to build a logic on top of it, which we can then use to prove stuff with instead. Um, and the logic that we can build for, or one of the logics that we can build for deterministic programs is for logic, which builds upon these triples. PCQ, where P is some predicate on the states, and Q is also a predicate on the states, and C is a program. And roughly speaking, what it means is that for every starting state such that P is true, and the program terminates from the state, we have that the output state that the end predicate, the post condition, holds under this the output state. Or in other words, if P holds to begin with and we terminate, then Q holds at the end. So this is called often like conditional correctness. You need also to know that it terminates to actually know that it's good. But for many applications, this is good enough because if you have non-termination, then you'll notice, right? But you can also have different logics where you deal with total correctness instead, where you also prove termination. Yeah. So that's what this thing means in the semantics. And now we can define some proof rules, which is what we can actually use then in things like EasyCrypt to prove things, and what we can then use as a kind of a higher level abstraction to also prove things for these analyzers and so on. So for example, if we have some statement hold to begin with and we don't do anything, then this predicate will still hold at the end. And for assignment, if we have some P, which may, some predicate, which may talk about X in some ways, then we can have as a precondition the same predicate, except it talks about the expression that was assigned to X. So some find it a bit confusing that the substitution happens in the precondition rather than the postcondition. But this has to do with substituting with X rather than substituting with the expression and so on. So yeah, we can't talk about X really at the beginning because X could have been anything to start with, right? But at the end, we might as well talk about X. It doesn't matter whether we talk about X or whether we talk about E because they're now the same thing, right? But at the start, we have to talk about E instead. And then we have sequential composition, where we have two programs, F and S, and we have some middle predicate Q. If we can prove that the precondition P, if we then evaluate F, then this middle condition holds, and if the middle condition holds, and if we evaluate the rest, then R will hold, then we can prove that this composition also is valid.
So
And
we talked
so
about
on.
this earlier, but can you repeat again the intuition behind what goes above the line and what goes below the line?
Oh yes, sorry. So this is a common notation for logics used, and what it basically means. This is a proof rule. Is what this is. Some assertion at the top and one at the bottom, and what it basically tells you is if you can prove these things at the top, then you know the thing at the bottom. Yeah. So logicians like to distinguish this from just having an implicit implication with assumptions, because this is something that you use in the when building your proofs rather than just being an axiom. Kind of the distinction there, right? So you could just say, no, we have modus ponens, and then we can just represent all of these using implications instead. But that's not how it's done usually in the logic community. And also it allows this to be represented kind of, yeah, rendered a bit neater sometimes, because now you can place them side by side and up and so on. Yeah, makes it more obvious where the post condition is under the line. Yeah. Okay. Yeah, and for if statements, you're allowed to assume that the if condition is true for the first one program, and you're allowed to assume that it's false for the second one, and then you need to prove that in both of those cases, you reach the post condition. Yeah, and then there's a conflict rule. You're allowed to strengthen preconditions and weaken post conditions. I think that's the. I think there might. I think it's the other way around. You're allowed to uh, strengthen preconditions and weaken post conditions. Maybe that was what I said. Anyways, um, yeah. And for the while loop, you need to show that the thing inside of the loop, if you have some um, if this B is true and you have the starting condition, then after you run C, you end up with P, and then you can know that in the post condition P is still true because this is preserved by each evaluation of C. And you also know that B is no longer true because you've exited the while loop. Yeah. So this allows, sorry?
That's just a basic loop invariant, I guess, the P.
Yeah, exactly. So this is kind of where these invariants come in, right? It allows you to do modular reasoning. You can split up your programs, and you can now reason about the contents of a while loop instead of reasoning about the entire thing, and or reasoning about limits in some partial order. Yeah, you can now reason about this smaller program. So that's the main idea of these logics, is to allow you to do modular reasoning on your programs. Yeah, and then for abort, if you have the predicate that's always true at the beginning, then after you abort, you can have the predicate that's always false. And the reason this works is because you don't terminate, so this statement here is vacuously true because there is nothing that you reach a bottom anytime. Yeah, so this was deterministic programs, but for cryptography, we're not interested, or at least in many cases, we're not interested in probabilistic program in deterministic programs. We're interested in probabilistic programs that might do random sampling and so on. So, oh, sorry, I forgot about this slide. Some results on these four triples that are interesting from like a logic perspective. Observation is that not all of these triples are provable. For example, if we can prove that if we have true at the beginning and then evaluate some program and then we have false at the end, this is the same as proving that C does not halt. So if you could prove this generically, then you could solve the halting problem. So we can't prove that. And for this other one, if we have some starting predicate, which is always true, and then we do nothing, if we can then know that we have P at the end, where P is, say, the Goldbach conjecture, if we could prove this statement, then we've proved the Goldbach conjecture. So yeah, we can't prove this kind of statements generically either. But it turns out that this is entirely inherited from the ambient logic, and we have this result, relative completeness. And often nowadays in the literature, they just say completeness instead, but this is often what it means in these program logics, is that if you have an oracle for statements in the ambient logic, some maybe first order logic that's used to prove all the statements that are not talking about programs. If you have an oracle for those, then you can prove things for prove any valid triple. So that's neat. That means that you don't need any more rules. The ones that you have are sufficient. At least if you're only interested in proving them to be valid and not invalid. But that is usually the case. You're interested in proving the properties of your program. Yeah. Okay. And now we get to probabilistic procedures. As mentioned, we are interested in proving things about probabilistic procedures. And to do this, we need to model things differently. Now we no longer can just talk about an output state because a program can do samplings from some distribution. You see a bunch of different models here. In EasyCrypt, for example, you allow sampling from an arbitrary distribution in the ambient logic, defined in the ambient logic. In some languages, you will see that they only allow coin flips, for example, and then build everything on top of this. But it all like ends up being doesn't really matter for the logic that you get out at the end. Yeah, but the main thing is we now need distributions instead. And you might have noticed that I now removed this bottom symbol from this thing, and this is a hack that's often done to make things simpler to reason about. Instead of having distributions over the state and non-terminations, we have just subdistributions instead, which means that they don't have to sum up to 1 anymore. They can sum up to something less, and then the leftover part kind of symbolizes non-termination instead. And this gives you better algebraic properties and so on. But something to keep in mind. Kan du gå ut, takk? Yeah. And now we need to define the semantics for this new language with the sampling as well, and also redefine everything we had already, because that was defining what happened for a deterministic language. But for those, the semantics is fairly obvious. Yeah. So when we sample, we check what the we take the distribution, evaluate it in the memory sigma, because the distribution is taken to be just an expression, which might include some program variables and so on. So you need to evaluate it in the current state. And then you say, what's the probability of getting y? And you substitute in the distribution that just takes in that is just 1 at the state where y is assigned to x and 0 everywhere else, and you sum up all of these subdistributions. And this summing, for example, is one of these nice things that you can do with subdistributions that you couldn't do for regular distributions. But at the end, you get another subdistribution, which then is what you have when you do random sampling. Yeah, and you also need to redefine all these other things. So for skip, you get a distribution that's just 1 for the state that you started with and 0 everywhere else. For abort, you get a distribution that's 0 everywhere. For assignment, you get something similar as with random sampling, except now you're not summing over all, you're just taking the 1 assignment to E. And for composition, you're summing over all the intermediate states. For if statements, it's basically exactly the same as for deterministic programs, and while loops as well, which is the reason we use this supremum operator, because now it's not just this simple partial ordering where we have one button symbol and everything else is just above it. Now you have subdistributions where the ordering is defined as if the probability of having some state is greater if all if for every state the probability of getting that state on the right side is greater than on the left side, then the distributions also the right is greater than the left. So we kind of take the pointwise comparison, and if the pointwise comparison holds everywhere, then it holds for the subdistributions as well. And by using this partial ordering, you can also take the supremum, given that it's defined, which it is in this case, because as before, you're only doing something extra for all of these aborting cases, which then might end up terminating when you give it more iterations to run.
So just a question about the previous. So why did in the if statement you now have perps and bottom, and I think previously you had a 1-0
Oh yes,
for.
sorry. No, this is left over from an earlier notation I used. Yeah, so it's
Okay.
supposed to still be 1 and 0. Yes, you're right. Yeah. I tried to match the syntax used by the quantum paper I'm going to have a short look at the end. That's also the reason for the leftover M in one of the earlier slides. In EasyCrypt, we don't talk about state, we talk about memories instead. So yeah. Yeah, and here we see there's also some more leftover stuff from this. Yeah. So using this semantics, we can define a bunch of logics on top of it. One example is this union bound logic, where you basically talk about the probability of some output condition holding. And this is quite nice because it allows you to use predicates still for the pre and post condition. And what this means is basically for all memories or states such that the precondition holds, we have that this sum, like um, the probability of it holding, the sum of the probabilities of all the states where Q holds is greater than or equal to P, basically. So yeah, the probability of Q holding at the end is greater than or equal to P, given that big P holds at the beginning. And you can define a bunch of rules. I'll just have some examples here. If you have, yeah, this is also supposed to be 1 and 0 again. If you have the true predicate at the beginning and you do some computation, then you will the predicate that's always false will hold with at least probability 0. In fact, it holds with probability 0, right? Because at the end, none of the states will make this always false predicate hold. So when you sum up all of them, you just get 0. Yeah, so that just means that these things are almost probabilities. They're greater than 0, right? But they don't quite act as probabilities because you're quantifying over all of the starting states. And you might have different probabilities depending on which state you start with.
So just a question about this, because if it's a probability, the PCQ or not, but if it would be a probability, then PCQ for all PC and Q would actually be at least 0 and at most 1. And then that line that you have there is just a special case of it.
Yes, exactly. Yes. So you have a similar result for 1 as well. And like I said, a bunch of other rules that you can derive from this. And this does get a lot more complex than for just regular for logic. I don't believe that union bound logic is proven to be relatively complete, for example. So you can always add some more stuff that also just for convenience, because sometimes you want a rule that's more of a special case or that is closer to the reasoning that you want to be doing instead of having to stack a bunch of these rules on top of each other every time. Yeah. Some of the rules look like the one on the right side, where you have multiple of these no, not triples but quadruples involved with different probabilities, and you can see how this starts to get hairy. And there's also a bunch of other logics that instead of having a precondition and a postcondition, they work with expectations, or they have they don't work with a starting state, but rather a distribution of starting states, for example. Yeah. So any question about this before we go on to the quantum part? All right. Yeah, so like I said, there's a bunch of other logics you can build on top of this. We also have logics that have two programs which you can use to prove that they behave the same way. Useful for if you have a specification and want to prove that your implementation matches that. And this is used widely in EasyCrypt, for example. But these concepts of building up the semantics and then deriving these simpler rules to use are kind of the main pointer, which is what all these formal verification tools rely on.
Right. So since you asked whether there are questions before you go into quantum, so at some point you had that you summed over the values of y. So and you talk about probability distributions. So are you expecting that all the variables can only have come from a finite set effectively?
So what you do is you assume that things are countable.
Right. So
Yes.
this is when you go to quantum, then that's one challenge you'll immediately face, I
Exactly,
suppose.
exactly. This is one of the challenges, yes. Is that
Okay.
now you have quantum state, which is not countable because you have, I mean, you can probably approximate it with the countable
Mhm.
stuff, but yeah. Um, so this is one of the issues, yes. Because now you can no longer do this nice thing of having a predicate at the beginning and a predicate at the end, because you're talking about this quantum state. And in fact, what they do in this paper about classical quantum state and programs, because there are some papers which work directly with quantum computation, but as far as I can tell, um, it should be easier to deal with or prove things about your programs if you still have part classical reasoning, because you can use all these existing proof techniques. And usually what you will have is you will have some component that's quantum, and you will be doing some classical stuff, and then you will be running the quantum again. And the end result that you're actually interested in will be purely classical often, like for Shor's algorithm, for example. Um, so you can conceivably at least simplify your results and proving process by considering classical quantum programs instead of considering just quantum programs and then doing some reduction between them. All right. So yeah, what they do in this paper is they have these different paradigms that they explain. They start with the classical, which is exactly the same as this Hoare logic I explained, and then they have a probabilistic setting. But they approach it slightly differently, exactly because of what you mentioned, where you have uncountable states, so you can't use the same reasoning as before. And because of this, they use an expectation-based logic instead, where you want assertions to be functions from states to the set of 1 or 0, but here instead it's a function from 0 to 1, and then you can sum up those and compare the sum in the at the beginning and at the end, to prove these quantum Hoare triples. And they continue doing this with quantum as well, where they use density operators. And here they do the same trick as with probabilistic, where they use partial density operators instead of using the regular density operators, so they can collapse non-termination into this. And what this means here basically is just that the trace doesn't have to be 1, it can be between 1 and 0 instead. Uh, and yes. And yeah, they have these they use observables to symbolize these assertions. If you have some state, then you will get some values out at the end, and then you can use the expectation for this observable in this quantum state to and compare those at the beginning and at the end. And that is what the triples mean here. Yeah, and then they have this huge, larger language where they add assignment of quantum variables, where they are resetting the quantum variables to 0. They have multiplication by some unitary matrix, and they have measurement is what they add beyond what's in the probabilistic case. And here, nicely syntactically, you just get for free that you can't have any cloning and all this other business, because all of these operators only have one quantum variable. You don't have assignment from one quantum variable into another one. If you want to use the same quantum variable in one place and another place, you just have to use the same variable. And probably you can build some abstractions on top of this to avoid this limitation. But yeah. So you can do this extension. It gets very complex. I barely understand any of this myself, but this is kind of a look forward to what we can do even with quantum computers. For my purposes, just proving things about our post-quantum schemes is what's most interesting. Because for formal verification, to a large extent, this is very time-consuming, and even for deployed schemes, you have to choose which ones you want to formally verify, because this is a large undertaking. But there are some that have been formally verified. For example, there is a formally verified implementation of Kyber in a programming language called Jasmine, which then translates to EasyCrypt, which proves that certain properties hold about the program. And going back to this slide, one of the things that you can do with some more purpose-driven programming languages that you can't do if you tack on something to C or tack on something to Rust is with constant time, for example, because these compilers are not built to preserve constant time properties. So what you do in practice then for constant time is you check the output assembly, and if it's not good enough, then you write out assembly yourself and use inline assembly. And of course, this isn't that great for formal verification either. So they have languages like Jasmine, which are lower level and don't do optimization really, but still abstract on top of machine code, and then are designed to preserve constant timeness as the best effort, at least, because there's limited guarantees from from hardware vendors. Yeah, so some things you can do with formal verification. Yeah. Yeah, and yeah, using this quantum semantics, you derive a bunch of rules. Don't ask me to explain any of this, but yeah, there's many different approaches to this being done. Yeah.
Okay, so oh, questions. Yes, great. But for the post-quantum setting where you are proving security against quantum attackers, let's say QROM, right, where you actually do need to use some quantum physics, you still don't need to go to this quantum Hor logic, as I understand.
So if you want to prove things in the random oracle model, There was a paper a while ago that did this for EasyCrypt that tried to give you access to random oracles, but for it was limited in what you could do with them. So as far as I understand, you couldn't write any reductions that actually did anything quantum, which then meant that you couldn't use it in some proofs. They did prove some things using this system, but for example, there is a line in the formal verification of dilithium, which says we wanted to use this QROM in EasyCrypt, but we couldn't because it didn't fit our purposes. So that is a limitation that doing QROM formally verified is difficult. There are some tools that go further with this, but not in EasyCrypt right now. And this previous paper has been because of these limitations, the work that was done there is not integrated into mainline EasyCrypt. And as far as I understand, these tools in other places are not used widely for cryptography. There's enough challenges already with just the ROM for formal verification, sadly.
Yeah, that makes sense. Unless there is somebody else, I will shoot ahead with a quick other question. We're slightly over time, so if anybody has to leave, just go ahead. But I was wondering where you introduce this table comparing the different paradigms. So I was trying to understand better what is happening in the classical quantum world.
Yes.
What is the notation saying here, and why does it make things easier?
Okay, so what they do basically is you have every state or every classical state, sigma, has some density operator associated with it, and the trace of this density operator is the probability of this classical case. Yeah, so the sum of the traces of all the density operators should be less than 1, basically. So this is very similar to like a distribution of classical and quantum states.
Yeah, that makes sense.
Except for algebraic reasons, they do it like this. I also don't fully understand why they work with density operators everywhere, because they could be using state vectors, I think, in the preconditions or for the pre-state. Because as far as I understand, and correct me if I'm wrong on this, you use the density operator because of measurement, because you end up with a probability distribution of quantum states when you do measurement.
Yeah, this is true, but the density operator formulation is fully general, so it might be easier to just stick to one formalism. The other thing
Yes,
is that it allows you to talk about subsystems that may be entangled with each other without having to always argue about the full system, and this you can't do with state vectors.
sure. Yeah. But as far as I understand, you have access to the entire system, at least in this formalism. But maybe there's some stuff you can do where you can have rules that only talk about some of the variables that wouldn't work otherwise. Yeah, that
Yeah.
might be right.
Okay. Yes. Okay. But are there any more questions, or should we leave it there?
No, not for me. I mean, thank you very much, Oskar, for a wonderful talk. I mean, really appreciated it. Very insightful as well. So,
Thank you.
uh,